Hello, people. This is Mr. Tolbert's class. This is Chapter 18, Lesson 2. Chapter 18, Lesson 2. In this lesson, we're going to be hitting these particular goals. We'll contrast a recipe with the chemical equation. We'll explain why reactions can be limited or have excess amounts. We're going to be able to write, and we're going to write the equation for percent yield, and we should know how to find percent yield. We're going to learn about how to change the rate of a chemical reaction and what components in a chemical reaction can actually speed it up or slow it down. And then we'll talk about equilibrium. Is there a balance with chemical reactions, which means going one direction, is there a way to go the other way? Is there a way that a reaction can happen at the same time, at the same speed, the opposite happen? That answer is yes. So chemical reaction systems, here is the recipe for some chocolate cake. You got like a cup of flour, some sugar, half cup milk, one egg. Peep this. Look at the bottom. It says here that this makes how many servings? 8 servings. But let's just say you only have 4 people. Let's get to that in a moment. Now here's the same recipe, except this is the recipe for water, which is going to require so much hydrogen, so much oxygen. But what if you only have a couple units of hydrogen? What do you do? What is there? Let's talk about that. We're going to talk about how and why we balance these chemical equations. So, to make a good tasting cake for half the people, if the original recipe said for 8 people, but I'm only throwing a party for 4, you don't want to make that much cake because you don't want to throw it all away, even though everybody loves some cake. So what you're going to do is you're going to take the entire recipe and you're going to half it. You're going to cut it in half. So you would have to use half as much of the other ingredients to make half the cake. By halving the recipe, you'll make 4 servings of chocolate cake rather than 8. You can do the exact same thing when you're talking about making water, when you're talking about these other chemicals that we can put together. A balanced chemical equation shows the ratios of the number of molecules of reactants needed to make a certain number of molecules of products using these coefficients. Here in this particular picture, you can see that I have so many reactants. I've got like 4 molecules of hydrogen and only like 2 molecules of oxygen. When you put it all together, we know it's H2O, so it's 2 parts hydrogen for 1 part oxygen. If we put them together in the right amount, it looks like we have the exact amount to come out with 4 molecules of water. But what if you were missing one? If you were missing one, you just wouldn't have enough to make an additional water molecule. When a balanced equation doesn't tell you, a balanced equation does not describe the exact conditions under which a reactions will occur. The right conditions for most of the reactions are used in science and the industry are a result of careful research and experimentation. Limiting and excess reactants. When a chemical reaction occurs, I didn't end my first lesson. Oh, I am in the second lesson. Sorry, guys. Sorry. When a chemical reaction occurs, the reactants are not always present at an exact ratio by a balanced equation. What usually happens is that the chemical reaction will run until it has no more stuff to keep on running. The reactant that is used up first in a chemical reaction is called a limiting reactant. The limiting reactant limits the amount of product that can be formed. So here it has a question. It says, which reactant will be used up first? You really can't know from this picture because you don't know if it's 2 parts of the stuff in the bottom, solution A, to 1 part, solution B, or 4 parts of it, so you really can't tell from that picture. Limiting and excess reactants. A reactant that is not completely used up is called an excess reactant because some of it will be left over in excess after the reaction is complete. Now, this next concept, what's called percent yield. Percent yield is going to give us a real measurement of how much can you actually make based on the amount of how much cake can you make based on the amount of groceries you went to the store to get to make your cake. That's the percent yield. Often the amount of product you are able to collect and measure is less than the amount you expect. We call that sometimes experimental error, often affects how much product is produced. But it's not a perfect world. So you're not always going to have the right amount of all of the raw materials to do everything that you may need. Here, copy this slide, please. Percent yield. Percent yield is exactly what you see here. It is the actual yield divided by the predicted yield, and then you multiply that number by 100. So write this down, please. Thank you. Example of how percent yield on a sample. Aspirin can be made in the laboratory through a series of reactions. If the actual yield for aspirin was 461.5 grams when the reactions were performed, and the predicted yield was 500 grams, what is the percent yield? So what you came with at the end of the day was 460 grams. What they told you was going to make was 500 grams. This is where you use percent yield. Here we go. So we're looking for yield of the reaction. We take my amount that actually we measured, and you divide that by what we predicted. Whatever number you have, you're going to multiply that by 100. And that's the difference. The difference is from what you had, you only made 92.3% based on the materials that you actually had. What about reaction rates? What about speeding something up or slowing it down? Like we're talking about with kinetics, we're talking about movement. In all phases of matter, atoms and molecules exhibit random motion. This concept is part of the kinetic theory of matter. The speed at which atoms or molecules move depend on their state, as we've talked about before. If they're moving faster, more energy, you know how it works. Slower, less energy. Here we go. So the reaction rate for a chemical reaction is the change in the concentration of the reactants or the products. Remember, folks, the reactants is the stuff that you start with versus the things that you end with. So you have the stuff you start versus the stuff you end with. So you can measure those rates. Here's how. First, you can add heat. So speed it up, speed it up. If you speed it up, it should go through a chemical reaction a little bit faster. Or you could have more to start, have more product, have more things, have more recipe that you went to the store to get in order for you to make more product. Or you can position the reactants in a way that they're going to run into each other, that you have a more likelihood to create that product. And the thing that does that, and it does it in biology, but it also does it in chemistry, they're called catalysts, and they are crazy smooth, okay? Enzymes in your body, folks, are catalysts. These are special mechanisms that help speed up chemical reactions, but they're not consumed in that reaction. What they basically do is they hold a molecule in a certain position so that it's more likely to react. A catalyst is a molecule that can be added to a reaction to speed it up. Catalysts work by increasing the chances that two molecules will be positioned in the right way for a reaction to occur. Here you've got the reactants, the reaction, and the products, right? So what a catalyst does, this green thing here, is it puts this A and B together, just hold it just long enough that there might be a reaction there. That's what your enzymes do in your body. They're catalysts. What about equilibrium? Is there a balance? Forward, reverse, upside down, all these things. A reaction may reach what we call chemical equilibrium, a state at which the forward rate or the rate of forward reaction is going to equal the reverse of that reaction. If you have an A plus B gives you AB, the opposite would be AB turning back into the individual A's and the individual B's. In chemical equilibrium, the reaction can proceed both left and right simultaneously. So as it's going this way, making the AB together to make a combination, this way to break it apart. It happens at the same time. Pretty cool. Equilibrium. And that is the end for lesson 2.